Okay, so any phase change question will be asking about how much energy it takes to go from one phase or one temperature of a substance to another. In this example question, we're talking about how much energy is required to take water from negative 15 degrees Celsius, which would be below the freezing point, so ice, to 110 degrees Celsius, which is above the boiling point, or into the gas form or steam. Now, whenever you're doing a phase change question, you always want to draw a graph to help yourself map it out. The graphs always have the same setup. So let's draw one down here. They always start with the diagonal part. They always have a flat part, another diagonal, another flat part, and then another diagonal going up. This graph has got energy on the bottom and temperature on your y-axis. Your flat parts are where your substance melts and boils. So the boiling temperature and the melting temperature should be added to the graph. So water melts at 0 degrees Celsius and boils at 100 degrees Celsius. That lets us have a starting and ending point for where we're going to be for this question. Since we're starting at negative 15 degrees Celsius, we need to start below this 0 degree point, somewhere down here. So we'll call that negative 15 degrees Celsius. We're going up to 110 degrees Celsius, which is above our boiling point, so somewhere up here. We'll call that 110 degrees Celsius. So on the coldest part, the lowest temperature, we have the solid form. Then this part's when it's going to melt. Energy is going in, but the temperature is not going up. It's flat. Then once it's all melted, that solid has melted into a liquid. Once the liquid gets up to the boiling point, it, well, boils. Once it's all boiled, it's all done there, it's all turned from a liquid into a gas. Those are the 5 parts of every single graph for a phase change question. Now we need to put the math in here, and some of this useful information we've got up here will tie into it. So this is going to be our starting point, and this will be our finishing point. So every time we change, if you pretend you're a car on this slope and you're driving up, every time you change direction, there's going to be a new equation we use. All of our diagonals will have a similar equation, and all of our horizontals have a similar equation, so there's really only 2 equations when we do this. Our first part is going diagonally from the starting point up to this change in direction. That first one is what you've seen in the first section of Unit 9. Energy equals mass times specific heat of a substance times a change in temperature, or T2 minus T1. There's a similar form in the back of your periodic table for this use. So our first one is going to be energy equals the mass of the substance, which we didn't actually put in this thing, so let's just say the question said take 200 grams of water from 15 degrees Celsius, negative 15 Celsius to 110 Celsius. So our mass will never change. We always have the exact same mass of that substance in every step of this. So 200 grams, that's our mass, times the specific heat of the substance. So that's going to be unique to every substance in every state of matter. So if it's a solid, liquid, or gas, that will change. So when it's down here into solid water is called ice. So we need the specific heat of ice. We're going to use this as our specific heat. So 2.03 joules per gram degrees Celsius. That's the unit you'll probably see most often for specific heat. And note, our grams will cancel. One's on top, one's on bottom. That'll come in handy because we want our final answer to be in joules. then times our change in temperature. So we started at negative 15 degrees Celsius, so that's our T1, so minus negative 15 degrees Celsius. And we're ending at the melting point, which for water is 0 degrees Celsius. So it's 0 degrees Celsius minus negative 15. Note that double negative will make it positive when you put it in your calculator. And this Celsius will also cancel this one, which means that cancels, and that cancels. We're left with just joules. So energy for our first equation, let's pull up my calculator, will come out to 200 times 2.03 times 15. I get 6,090 joules. That's the energy it took to get from negative 15 degrees Celsius solid to 0 degrees solid. But we're not to our finishing point, so we keep going. So equation 2, now we're on a flat part. So the equation will not be the same thing. It's going to be what's called the heat of fusion. Heat of fusion is when you're going to or from a solid. That's the information they give us up here on this third line. Heat of fusion of water's got a number in joules per gram, joules divided by grams. So we're going to use that as our energy. So energy equals 333 joules divided by grams. And then since our energy should be in joules, we just have to multiply by grams to make that unit cancel, and we've got our energy. So like I said, our grams hasn't changed. Our mass will always be 200 grams. Grams will cancel. So if we take 200 times 333, we get the energy it took to melt that substance, 66,600 joules. I'm going to underline my partial answers just so I can find them later. So now we've gotten from here to here. Step 1 got up to 0 degrees. Step 2 melted it. It's still at 0 degrees, but now it's all liquid. It's liquid water. Next step, we've got to heat that liquid water up to the boiling point. So note a diagonal line, which means we go back to our MC T2 minus T1 equation. So 3, energy equals the mass again, which is our 200 grams, times the specific heat of liquid water. So liquid water is not actually given here, but it is given on the back of your periodic table. So it's one you might just know by doing it enough. 4.814 joules per degree Celsius. Everything else will be given to you in a question. That was our M, our C, our change in temperatures. So our final temperature is going to be up here at the end, which is our boiling point, which is 100 degrees Celsius. So that's T2. So 100 degrees minus our starting temperature is the melting point, which is 0 degrees Celsius. So 100 minus 0 is just 100, but it'll let our units cancel. So now when we do this, we'll take our 200 grams times 4.184 times 100 minus 0, which is just 100, and get our energy it took to bring it from 0 to 100 in liquid water form. That calculates out to 83,680 joules. So that gets us from, we've done step 1, step 2, step 3. We're not yet to our finish point, so we now have to do another horizontal one, which is going to be a heat of something. We did heat of fusion already to fuse it as a solid. Now we need to vaporize it, go from liquid to gas. So we need the heat of vaporization. So 4 is going to be this number, our 2,260. Note it takes a lot more energy to vaporize than it does to melt something. And again, it's joules divided by grams, so we multiply by our grams, our mass, to make those cancel and get just joules. So 200 times 2260, or 2260 times 200, gets us 452,000 joules. That's the energy to get from liquid water 100 degrees Celsius to gaseous water 100 degrees Celsius. We're almost to our finish line, but not quite. So there's a fifth step. Since it's a diagonal again, we go back to our MC T2 minus T1 energy equation. So again, the mass is still and always will be 200 grams times the specific heat, but now our specific heat is water in the gas phase, so as steam. So we need the specific heat of steam, 2.06 joules per gram degrees Celsius. And again, our T2 minus T1. T1 is where we left it at 100 degrees steam, so that's T1. T2, we're bringing it up to our goal of 110 degrees Celsius. So our final is 110 minus 100, which will come out to 10 degrees. When we solve this, we'll take our 200 grams times 2.06 joules per gram degree Celsius times, in parentheses, 110 minus 100, which comes out to 10. And it gets us 4,120 joules. That's how much energy it took to get from steam at 100 degrees to steam at 110 degrees Celsius. We've gotten from our start to our end. We're basically all the way there, except we need the total energy to do all those processes. So now we add those 5 up. Energy in step 1 plus energy in step 2 plus 3 plus 4 plus 5. So energy total equals 6,090 joules plus 600 joules plus 83,680 joules plus 452,000 joules plus 4,120 joules. When we sum all those up, we should get 612,690 joules. But joules are a very small unit, and talking about them in the hundreds of thousands or millions of joules is not usually how we go about this. So usually we convert our joules into kilojoules, which is always the same conversion factor. Oops, 90. Try one again. There's always 1,000 joules in 1 kilojoule. So when we do that, it equals 612.69 kilojoules. And that would be our final answer for this question. Hope that helps.